All right, everybody, so this is going to be Scale 3 and Scale 4 of Unit 4. We're going to be talking about heat calculations. So heat, which is represented by the letter Q, which is kind of annoying. We would hope it would be represented by the letter H, but it's not. It's a letter Q, is energy that is transferred from one substance to another because of a difference in temperature between them. It always flows from an object at a high temperature to an object at a lower temperature. And specific heat of a substance, which is represented by the symbol C, is the amount of energy required to raise the temperature of 1 gram of the substance by 1 degree Celsius. And the specific heat of water in the liquid phase is 4.184 joules per grams degree Celsius. Now, this fact that this is the specific heat of water is something that you kind of have to have memorized. So if you're like, man, I'm missing that piece, well, it's because you're supposed to know it, or at least know that you're supposed to look here. And the fact that its number is so high compared to other substances is why it takes water a really long time to heat up compared to other things. So for example, most metals have a specific heat of about 0.1, and so compared to 4.1, that's almost 400 times more energy to increase water by 1 degree than compared to most metals. And you can do a calculation to determine how much heat has been absorbed or released using the formula Q equals mass times specific heat times change in temperature. Now, the symbols for those, so mass is the letter M, specific heat is a capital C, and change in temperature is delta T. Now, the change in temperature is calculated using the formula delta T equals T final minus T initial. And so I kind of break it up this way. So Q equals M times C times delta T. And your delta T is equal to T final minus T initial. Now, before we get started, I want to remind you that your units for these measurements are how you determine their labels in a question. So when you have Q, M, C, and delta T, right, or any sort of temperature number, so if that's your symbol, right, and you have your unit, oh, there's neither. Q has the unit of J, which is joules. M has the unit of grams. Specific heat has a combination unit of joules / grams degrees Celsius. And then your temperature values are going to be degrees Celsius. Now, keep an eye out and don't get tricked by this. If you see degrees Celsius, that means it's temperature. But if you see a capital C, then that's talking about joules per grams degrees Celsius, and it's something different. So that degrees, the little circle, makes all the difference. So as we look at our example question, it says calculate the heat. Okay, that's what they want us to do. Calculate the heat. We know that heat is Q. So that's what we need to know. It says calculate the heat that is being absorbed by a 15-gram piece. Okay, we got a number. And there's a G. G is for grams. And if we check, that means it's represented by the symbol M. So that's our mass. And it's a piece of cadmium while rising from 24 degrees Celsius. Okay, well, that's a temperature to 62.7 degrees Celsius. Again, a temperature. And we know that since it's starting at 24 and rising to 62.7, we can say that this is our initial temperature, or the temperature at the beginning, and this is our final temperature. And they tell us that the specific heat of cadmium is 0.231 joules per grams degree Celsius. So this is capital letter C. for our formula. Not a degree C, just a capital C. So when we look at our two formulas, we have Q equals M times C times delta T, and we have that delta T is equal to T final minus T initial. So let's go ahead and do that first. So delta T is equal to T final minus T initial. So that means our change in temperature is equal to 62.7 degrees Celsius minus 24.0 degrees Celsius. Now remember, your units are actually really, really important, so don't forget to write them down. So when we subtract this and we say 62.7 minus 24.0, you get 38.7 degrees Celsius. And now that we know our delta T, we can actually solve for Q using our Q equals M times C times delta T formula, because we're looking for Q, so it has to be by itself. And luckily for us, our formula already has Q by itself, so we don't have to rearrange or anything. We literally just have to multiply our three numbers. So Q would be equal to our mass, which is 15.0 grams, times our specific heat, which is 0.231 joules per grams degrees Celsius, times our delta T, which we already subtracted to figure out, which is 38.7 degrees Celsius. Now, what's important to notice is the units. Like, since we have grams and grams here, they cancel out, and degrees Celsius will cancel out. So that leaves us with the unit of joules, or capital J, which is good because Q, if you remember, Q has the unit of J. So that's all that should be left if we did our problem correctly. And so all that's left for us to do is, we know it's going to be Q is equal to a certain amount of joules, is to actually just put it in our calculator. So 15.0 times 0.231 times 38.7, and that gives us 134.1 joules as our answer. And there are more practice problems for these on eClass in your independent practice, as well as the Unit 4 tests and quizzes. So if we know this formula, it actually allows us to do some really cool things, because it allows us to do the math for a calorimetry experiment. Now you might be saying, Ms. Nichols, what is calorimetry? That I'm not even sure I could pronounce that. And so basically what happens is sometimes we need to figure out how much energy is being released by something. And so we use calorimetry to do a couple of things. If you've ever seen a nutrition facts label on the back of something, it'll say, you know, oh, this Dorito has 150 calories in it. Well, did you ever wonder how? How do they know that? They did an experiment. There are things, there are people who have jobs where their title is they are food chemists. Their job is the chemistry that's in your food and cooking. And so these food chemists would do an experiment to figure out how much energy is released, because the calorie just measures energy. We can also use it to identify unknown metals, because if I have a block of a metal and it's silver in color, that doesn't really tell me much because there are so many silver metals. So you can do an experiment. And so basically what you do is, calorimetry is the measurement of the transfer of energy into or out of a system during a chemical reaction or a physical process. So typically the chemical reaction would be like your food. We basically like blow it up and catch it on fire, or a physical process like a block, like a metal block releasing heat into some water. And a calorimeter is an insulated container, so kind of like a a thermos that you use to keep your coffee warm during the winter. This insulated container has a lot of water in it to keep it insulated. And so we use it to measure heat changes. So in a calorimetry experiment, there are a couple things that we have to make an assumption about. So first of all, if you're doing the food experiment, you typically have a ring stand, and let's say you've got some water in a can here. Basically what you'd do is you'd take your piece of food underneath your experiment, you would light it on fire, and all of the heat would go into the water. Okay, good old H2O. Or if you have a piece of metal, right, and you're like, hey, I want to know what this is. Well, you would heat it to be really, really hot. And then you would take some water. In high school, we would typically use like a styrofoam coffee cup. I typically go to Quick Trip and get a ton of them before one of these experiments. And you take the really hot thing and you put it in the water, and then the water absorbs the heat, because if you put something that is really hot, like that metal, into the water is going to warm up, and we can measure the difference between it. And so one thing that we do is that we assume that all the heat that's produced is transferred to the water, meaning that the energy that is released by the object is all absorbed by the water. And we know this actually isn't what happened in real life, because, you know, when I take this metal piece of thing and I take it out of the fire and I put it in there, some of the heat is going to go into the air. But when we're doing a high school experiment, we kind of just have to make the assumption to make our numbers and our math easier. So what this tells us is that the heat that's released by the object is equal to the heat absorbed by the water. The number is the same, but the object will have this negative sign showing that it was released instead of absorbed. So if my metal releases 100 kilojoules of energy, we would put negative because it's releasing, and that would mean that my water absorbed 100 kilojoules, so it would be positive. So it's the same number, just one is positive and one is negative. And the second assumption that we make is that the final temperature of the water is the same as the final temperature of the object. Now that's specific for this type of experiment, because when you put the metal block in here, the water, right, if you have a thermometer, this is my beautiful drawing here, if you have a thermometer, the thermometer is gonna start to go up when you put that thing there, and eventually it'll reach the highest point, and that's where the water and the block are the same temperature. And then they'll eventually both start to cool down to match the temperature of the air. But what this tells us is that T final of my water is equal to the T final of my metal or my object. And so that is another really important thing when we're doing these calculations. So if we look at this first and only question on your study guide, it says we have a piece of metal weighing 95.48 grams and was heated to 103.24 degrees Celsius and then put into 142.24 grams of water that was initially at 20.40 degrees Celsius. Now, in this first sentence, we already have 4 different numbers about 2 different things. So in order to be successful in this kind of problem, you need to separate the numbers that they give you about your metal from the numbers that they tell you about the water, because you're going to have 2 steps, one that deals with the water and the second one that deals with the metal. So here it says we have a piece of metal weighing 95.48 grams. Now, since we see that G, we know that this is going to be our mass. So M is equal to 95.48 grams. And it was heated to 103.24 degrees Celsius. So we know that this piece of metal initially is at 103.24 degrees Celsius. It says it was then put into 142.24 grams of water. So again, we see a G for grams. So now we've got our mass of our water, which is 142.24 grams. And it was initially at 20.40 degrees Celsius. So we have a T initial of 20.40 degrees Celsius. So we can see that the metal is really, really hot. The water is at about room temperature. And it says the metal and the water were allowed to come to the same temperature. So they put the metal into the water and they reached the same temperature, which was 32.96 degrees Celsius. So we know that the final temperature of my water is 32.96 degrees Celsius. And here's the thing, they tell you it's the same temperature, but also remember, for our experiment, we said that the metal and the water have to be the same final temperature. So that means I can also put that in my metal category. So it's 32.96 degrees Celsius. So we see that over time, the metal cools down. It goes from 103 to 32 degrees, whereas the water heats up. It goes from 20 to 32 degrees. And then it says, assuming no heat loss to the environment, calculate the specific heat of the metal. So they want to know, okay, what is C of our metal? Not degrees C, but just C, the specific heat. Now, in order to solve this, they actually did not tell you a really crucial piece of information that you need in order to calculate this. They didn't tell you the specific heat of water because remember up here, we talked about how you had to have that memorized, how the specific heat of water is 4.184. So that's something we expect you to remember. So the specific heat of water is 4.184 joules per grams degrees Celsius. That's just what it always is, no matter what type of problem you're doing. So step one, when we want to solve this, is our goal, in order to figure out what C is, we have our mass, we have our temperature, we can actually calculate our delta T, but we have to know what Q is as well because we're going to have too many missing variables. So in order to do that, we use our first assumption that Q of our object is equal to Q of our water. So since we have the mass, the temperature, our specific heat, we can actually calculate the Q of water. And so that means you have to use all of your numbers in your water column. And we want to go ahead and calculate our delta T for our water. So that would be 32.96 degrees Celsius minus 20.40 degrees Celsius. It's always, always, always the final minus the initial. And when you do that, we see that the change in temperature for our water is a positive 12.56 degrees Celsius. So when we calculate Q of our water, okay, Q of water, so I'm going to put a W there, will be equal to the mass of my water times the specific heat of my water times the change in temperature of the water. So it's going to be fairly simple. We just plug in our numbers. It's 142.24 grams. I'm going to put it in parentheses to keep my units together, times the specific heat of water, 4.184 joules per grams degrees Celsius, times my change in temperature, which is 12.56 degrees Celsius. And notice that we're going to have units cancel out. So grams cancel out with grams, Celsius with Celsius. And when we calculate this, 142.24 times 4.184 times 12.56, you get that Q of our water is equal to 7,474.86 joules. Now, we know it's joules for our unit because that's the only one that did not cancel out. So that's a lot of energy that it absorbed. And so we know that if Q of water is a positive 7,474 joules, what that tells us is that Q of our metal is equal to, so I'm going to move this over a little bit. That tells us that Q of our metal is going to be equal to a negative 7474.86 joules. So basically you put a negative sign in front of that for Q of your metal. And if we go ahead and calculate our delta T, and it's 103.24 degrees Celsius minus 32.96 degrees Celsius. I don't have a lot of space there. Let's see. We get 70.28 degrees Celsius. Oh, hold on. Does anyone see the mistake I just made? I just did my initial temperature minus my final temperature. That's not correct. Good job, Miss Nichols. So remember, it's actually always our final minus the initial. So it should have been 32.96 degrees Celsius minus 103.24 degrees Celsius. Now, the way I caught my mistake was I knew that my metal was cooling down, so I should have had a negative change in temperature. So when you subtract it that way, you actually get the same. You just get a negative 70.28 degrees Celsius. So then for I wrote step 1. So now when we do step number 2, we calculate the C of our metal using Q equals mCat, but now with different formulas. So Q equals M times C times delta T. And so when we plug this in, we know that we've got a negative 7,474.86 joules is equal to our mass, which is 95.48 grams, times C, which we don't know, times our delta T, which is negative 70.28 degrees Celsius. And you can simplify the right side. So if we leave the left side the same, which I just added a decimal there on accident, 74.86 joules. We simplify the right side by multiplying 95.48 times a negative 70.28, and that gives us negative 6,710.33 grams degrees Celsius, because we keep those units, times C. Now, remember, the goal is to get C by itself. That's what we're looking for. So in order to move this number here to the other side of the equal sign, you have to do the opposite of the math. So since it's being multiplied by C, that means you would divide by it on both sides in order to cancel it out. And so when we do this, we get that C is equal to, because, all that cancels out, we have a negative 74.86 divided by a negative 6710.33, and that gives us 1.11 joules per grams degrees Celsius, because these units here, none of it canceled out, so you keep all of it, which is great because that's what our units are supposed to be according to our unit chart here, right? C is supposed to have units of joules per grams degrees Celsius. So hopefully that makes sense. If you just write out all of your numbers into your metal and water column, and then do step 1, calculate Q of water, step 2, calculate C of the metal, you'll be just fine.